Hello everyone. In this session, we are going to see 8279 programmable keyboard or display interface. So in the previous sessions, we have seen interfacing keyboard using 8255 device where we have integrated both hardware and software approach. So in this session we are going to see this programmable keyboard interface using 8279. So this is a hardware approach where we are interfacing a matrix keyboard. So whatever we have seen, that is the interfacing keyboard using 8255 device, that was a linear approach. So this would be the matrix, that is where we have rows and columns of a keyboard, and a multiplex display, that is the electronic display. Now in the previous sessions where we have seen, that is interfacing keyboard using 8255, where we have used the software approach, that is instruction sets. So there we could find the disadvantage, that is the disadvantage there was the amount of time that was required to check whether the keyboard is pressed or not. Okay, so and also to refresh the display, where we have to read the new key, we have to refresh the display. So there the amount of time was taken more, that is amount of time was consumed there. So that was the disadvantage of using the software approach, that is the instruction set. So this 8279 will relieve that processor from these two tasks, that is amount of time in checking the keyboard and refreshing the display. So this problem can be over this problem we can overcome this problem by using this 8279 device. Now this also has a disadvantage using of 8279. This also has a disadvantage, that is here the disadvantage would be the cost. That is the using this 8279, since it is a hardware approach, it is expensive. So the trade-offs between the hardware approach and the software approach are the production cost versus the processor time and the software development cost. All right. So here is the block diagram of 8279. So this would be the block diagram, and here you can see the four sections. One section here is the keyboard section, the second section is the scan section, the third section is the display section, okay, the display section here, and the fourth section is the MPU section, that is microprocessor unit section. So these are the four sections we can see in the block diagram of 8279. So in this video I'm going to explain each section in detail. So let us begin the explanation with the first section, that is the keyboard section. So this is the keyboard section here. The keyboard section has 8 lines. You can see the 8 lines here, that is RL0 to RL7. So this can be connected to the 8 column of the keyboard. So you can see this keyboard section here, where you have RL0 to RL7 line, which is connected to the 8 columns of the keyboard. So you can see here extra 2 lines, that is control stop. So these 2 lines are extra here, that is the status of this shift key and the control key will be stored with the key closure. So the status of this, whether it is on or off, the status will be stored along with the key closure. So here the key is automatically debounced. So we have seen what is debouncing, that is eliminating the multiple entries. So this here the keys are automatically debounced, and the keyboard can operate in 2 modes. Here the keyboard can operate in 2 modes. So what are the 2 modes here? That is 2 keys, 2 key lockout or N key roll over. So these 2 modes are operated here. So let us see what is this 2 key lockout and N key roll over. So in the 2 key lockout mode, if 2 keys are pressed almost simultaneously, so sometimes it happens that we press 2 keys simultaneously, then what happens is only the first key is recognized based on some parameters. Okay, so only one key will be considered, that is the first key will be recognized. So in the N key rollover mode, what happens is simultaneous keys where we have pressed two keys at a time, though both keys are recognized and their codes are stored in the internal buffer. So here what happens in the N key rollover, both the keys, that is what we pressed simultaneously, what we press at a time, so the both the keys are recognized and their codes are stored in the internal buffer. So it also can be set up that no key is recognized until one key remains pressed. So here we can see that no key is recognized until only one key remains pressed. That is, both the keyers are recognized. Now, the keyboard section also includes 8 into 8 first in first out, that is first in first out RAM. Okay, that is, this RAM contains 8 register where each register is of 8 bits. So that is FIFO, that is first in first out RAM. Okay, so this keyboard section also contains this. Now, this FIFO RAM consists of 8 register that can store 8 keyboard entries. Okay, so 8 into 8. So we can store here 8 keyboard entries. So each is then read in the order of entries. That is which order? FIFO order, first in, first out order. Now, the status logic keeps track of number of entries and provides IRQ signal. So here the status logic, okay, keeps track of the number of entries. The status logic keeps track of number of entries and provides IRQ, that is interrupt request, provides interrupt request. So you can see here interrupt request, you have a FIFO RAM status. So what does this do? This keeps track of the number of entries, how many we have entered. So this keeps the track of number of entries and provides IRQ, that is interrupt request signal, when the FIFO is not empty. So when the FIFO is not empty, this signal this status provides the signal, that is IRQ signal, interrupt request signal. So here this is all about the keyboard section. So in general, let's brush up, that is it contains 8 lines which is connected to the column of the keyboard. It also has extra 2 lines that can be stored along with the key closure, and and the keys here are automatically debounced, and also it operates in 2 modes, that is 2 key lockout or N key rollover, where 2 key lockout reads only one key when we press 2 keys simultaneously, and in N key rollover both the keys are read simultaneously. So here it also has 8 into 8 RAM, FIFO RAM. Okay, so it can store 8 keyboard entries and in the order of FIFO, that is first in first out. So here the status logic, you can see this keyboard is also connected to the status logic, which keeps track of the number of entries, the number of entries, okay, the entries which is done here in the RAM. So this keeps the track of number of entries and provides IRQ when FIFO is not empty. Okay, so when FIFO is not empty, this provides a signal, that is IRQ, interrupt request signal. So this is all about the keyboard section. Now let us go to the next section, that is scan section. So here you can see in the diagram, the scan section consists of 4 lines, that is SL0 to SL3. So these are the scan section which consists of 4 lines, SL0 to SL3. Now what does this 4 lines do? This 4 lines scan is used to decode, that is using 4 to 16 decoder. Okay, 4 to 16 decoder, which means it is a decoder that activates only one of 16 outputs for each 4-bit input in the integer range 0 to 15. So what does this 4 to 16 decoder does? It activates one of 16 outputs for each 4-bit input in the integer range 0 to 15 and generate 16 lines scanning. So this scans, okay, this scans lines by using the 4 to 16 decoder. All right, now this lines can be connected to the rows of the keyboard. Here in the keyboard section, there's RL0 to RL7, which was connected to the columns of the keyboard. Here the scan lines, that is SL0 to SL3, that is connected to the rows of a matrix keyboard, and digit drivers of a multiplex display, that is the electronic display. So where these lines are connected, it is connected to the rows of the matrix keyboard and the digit drivers of a multiplexed display, the electronic display, what we can see. So these lines are connected to the digit drivers of that multiplexed display. So this is all about the scan section, which is used to scan the lines. Next section. So next section here is a display section. So here display section consists of 8 output lines divided into 2 groups. So you can see here the display section, where you can see here it has 8 lines, but those are divided into 2 groups. That is, one is A0 to A3 and one more is B0 to B3. Now this line can be used either as a group of 8 lines or 2 group of a 4. So these lines can be used either as a group of 4 or either as a group of 2 4 separate groups or as a whole, that is group of 8. So in conjunction with the scan lines for a multiplexed display. So this is in conjunction, that is it is attached with the scan lines. All right. So the display can be blanked by using the BD line. So here you can see the timing and control, that is it is providing the BD line. So this BD line is used to blank the display. That is we want to blank the display section. Then we can do this by using the BD line. This section includes 16 to 8 display RAM. So you can see here the 16 into 8 display RAM, that is it contains 16 register, where each register is of 8 bits, where MPU can read from and write into any of these registers. So this is all about the display section, which is used to display and which is divided into 2 separate groups, that is A0 to A3, B0 to B3, where we can use either as a whole or we can divide into 2 groups, and this display can be blanked, okay, where we can keep this display empty by using this BD line. And also it also contains the 16 into 8 RAM, where it has 16 register of each register is of 8 bits. So this is all about a display section. So the last section, that is MPU interface section. So where we can see this section includes 8 bidirectional data lines. So you can see here above the MPU interface section, it has 8 bidirectional section, okay, bidirectional lines, that is DB0 to DB7, and one interrupt request. Okay, so one interrupt request, you can see here one interrupt request, and 6 lines for interfacing, including the buffer address line 8 not. Okay, so you can see here 6 lines. Okay, the 6 lines interfacing, including the buffer address, that is A naught. So this is what this MPU contains. So what happens here is when A naught is high, okay, the logic of A naught, that is this A naught line, address line A naught is high, then the signals are interpreted as control word. Okay, so when the logic of A naught is high, then the signals are interpreted as control word. If A naught is low, if suppose the logic of this A naught is low, then it is interpreted as data. Okay, then this is interpreted as data. Okay, so the IRQ line goes high whenever data entries are stored in the FIFO. That is, we have seen in the keyboard section, IRQ line was provided when FIFO was not empty. So in the same way, this line goes high whenever data entries are stored in the FIFO. That is, it means that FIFO should not be empty. So this signal is used to interrupt the MPU to to indicate that availability of the data. Okay, so this IRQ line goes high whenever data entries are stored in the FIFO. So this signal is used to interrupt the MPU to indicate the availability of data. That is, it says whether the data is available or not. This indicates whether the data is available or not. So this is all about the uh, interfacing the matrix keyboard using 8279. Thank you.